The next 2 days, I'm sorry about my voice, it's still recuperating. We're going to be covering organic and biochemistry. Today we're going to hit organic chemistry. Thursday we'll hit biochemistry. I wrote the exam for this section already, and the way this one's going to work, organic and biochem are going to be solely multiple choice. There's just a lot of survey material. It's not going to be anything too in-depth. It's more of a general overview. Do you get the concept kind of a thing? Chapter 16, which was the oxidation reduction, that one will be part multiple choice, part short answer. So there's only 5 questions that you actually write stuff out on the test. The rest of them are multiple choice, true, false. This is usually the test that people score the best on because it's just a very glance over everything. It's not like getting into the nitty-gritty calculations so much. So that's kind of the outline for this test as we're going over this. So with organic chemistry, the main goals for organic chemistry are to kind of get a basic understanding as to what organic compounds are, and then a very general overview on how naming them works and how identifying different functional groups, which we'll talk about here in a few minutes. So it's just very general overview for this. Okay, so when we're talking about organic chemistry, this is kind of the intro through your textbook. We're talking about things that are around us all the time, things that we see, things that we use. You just don't realize that you're dealing with organic compounds. So, for example here, they kind of introduce you to organic chemistry by talking about smells. The smell of jasmine is produced by benzyl acetate, an organic compound. This benzyl acetate molecule, this is what benzyl acetate looks like. Organic compounds tend to be primarily carbon, hydrogen, and oxygen type compounds. So they're going to have lots of carbons, lots of hydrogens, usually a couple oxygens in there, and sometimes you'll see some nitrogens or sulfurs thrown in there as well. Okay, so organic molecules, once again, these are things that have carbon that are combined with several other elements. Triethylamine, this is one of the favorite scents that we all love to smell. This is the smell of rotting fish. So you get sweet smells such as jasmine all the way down to those nasty, rotting, body decaying smells. Those are all considered organic compounds. Carbon-containing molecules are responsible for the smell of the dead fish, like we said here, as well as the sweeter smells. A lot of like the banana smells that you smell, that's an organic compound. Almond, vanilla, those are all organic compounds.
So all organic compounds have a smell to them?
Not necessarily, because like alcohols are considered organic. So like ethanol, those they have a different kind of odor. They're more kind of burn your nose type thing. That there's gasolines. I guess they have an odor. I'm trying to think. I guess they all kind of have their own little unique odor. I'm sure there's some though that don't, like, because you get oils and fats and things are organic compounds too, and some oils don't really have that much of an odor.
Or they probably do, but we can't with our senses.
Yeah, our noses probably don't pick them up. Okay, so here's some more of the organic compounds. Like I was saying, vanilla is one of them. This is vanillin. This is what is responsible for the scent that vanilla has. Then you have cinnamaldehyde over there, which is in cinnamon. So you're looking at some pretty unique-looking compounds. And we'll talk about what all these are here in a few minutes. Okay, so the difference between organic and inorganic. In the 18th century, that's when chemists had actually divided the two classes of compounds into organic and inorganic compounds. There are millions and millions of chemical compounds out there, and so they kind of came up with this general consensus that this is how we're going to divide them, our carbon-containing compounds versus our non-carbon-containing ones. Up to this point in this class, we focused primarily on the inorganic compounds. So this chapter is just going to give us a brief overview on organic. Organic chemistry is usually a 2 to 3 semester class all on its own, so it's just a very brief overview. Organic compounds came from living things. Sugar, that is from sugar cane or sugar beets, that's organic as well. Inorganic compounds come from the earth. Salts are examples of inorganic compounds. So salts, remember, is any metal plus a non-metal. It can be anything. Okay, so once again we have our organic versus our inorganic. Okay, early chemists realized that organic and inorganic compounds are very different in their properties. Organic compounds are very easily decomposed. Inorganic ones, on the other hand, are more difficult to decompose. And you can just think about this just in practical, everyday life circumstances. If you try to decompose something like salt, you have to heat it really, really hot. Most of us can't do this in our kitchen. Whereas if you're trying to decompose sugar, you can burn it on the stove very easily. You decompose it into carbon and water. It's two different things. Organic compounds can be very difficult to synthesize, whereas inorganic compounds are very easy to synthesize. Usually organic compounds, when you're synthesizing them, you're talking about a multiple-step process, and it can be very complicated to do that. The origin and properties of organic compounds led them to postulate that organic compounds are unique to living organisms only. And they postulated that living organisms employed a vital force, which was a mystical or supernatural power that allowed them to produce organic compounds. They thought it was impossible to produce an organic compound outside of a living organism because the vital force is not present. So this is before they could synthesize organic compounds. This belief, which became known as vitalism, was thought to explain why no chemist had succeeded in synthesizing an organic compound in the laboratory. But that didn't line up too well. So then, the first organic compound to really be synthesized was urea, and yes, this is related to urine. In 1828, a German chemist named Friedrich, well, I don't speak German. Is it Böhler? Anyone speak German? Sure, we'll pretend. Proved that wrong. He heated ammonium cyanide, which was an inorganic compound, and it formed urea, which was an organic compound. So he formed an organic compound from inorganic just by adding heat to it. I don't know what that says. Urea was only previously isolated from the urine of living organisms, so he was actually successfully able to synthesize this organic compound. His experiment was a crucial step in opening all of life to scientific investigation, and then he showed that the compounds that compose the living organisms follow scientific laws and can be studied and understood as well. So we're going to spend a few minutes to look at carbon. Primarily, we're focused on carbon with organic compounds. That is, if there is no carbon in the molecule, you do not have an organic compound. That has to be in there. So the number of compounds containing carbon is greater than the number of compounds of all the rest of the elements in the periodic table combined. So we're talking about numerous compounds. One of the reasons for this is that carbon, with its 4 valence electrons, can form 4 covalent bonds. And recall that these Lewis structures, remember, this is the Lewis structure, just carbon by itself. We have our 4 valence electrons right there. Carbon always wants to have 8 electrons, so it will form 4 bonds somehow in order to get those 8 electrons. So you can have 4 single bonds, you can have 2 double bonds, you can have a triple bond and a single bond. You can have all different kinds of combinations to get those 8 valence electrons. A second reason for carbon's complex chemistry is that carbon, more than any other element, can bond to itself to form chain, branch, and ring structures. So not only does carbon bond with other elements, it bonds with itself as well. And the chains get to be incredibly long. When we're talking about fatty acids and we're talking about triglycerides that are in our bodies, we're talking about some carbon chains that have up to 20 carbons in them. These carbon chains can get incredibly long, and they can branch. They can do all kinds of things with them. So here, this is what we call a straight chain carbon compound, and this is propane. And so you can see it's just 3 carbons, and then all of those extra valence electrons are obtained from bonding with hydrogen. So you have hydrogens attached to each of those carbons. Over here, this is what we call a branched hydrocarbon, and this is isobutane. You can see that there's 3 carbons right here, and then we have a carbon that kind of shoots off down to the side in the middle. So this is our branched one. And then over here we have a cyclic hydrocarbon, and that's cyclohexane, where the carbon forms a ring. And so that's another type of hydrocarbon that we have. Remember, when we talk about molecular geometry with carbon, when we have the 4 single bonds, we have a tetrahedral geometry. So we're going back to that Vesper theory. So we have the tetrahedral when there's 4 single bonds. When we have a double bond and 2 single bonds, that's our trigonal planar geometry. And then when we have a single bond and a triple bond, we have our linear geometry. So always, once again, on all of these, you can see that each of those carbons has access to 8 valence electrons. So it has those 8 electrons on the outer shell. So it just does it in different ways.
There's never polar because there's never lone pairs?
No, it can't. You can have polar organic compounds. Yeah, like alcohols tend to be polar. It just depends. These are going to all be nonpolar because they're just carbon and hydrogen, and they're symmetrical. Okay, so hydrocarbons is our first class of organic compound, and hydrocarbons are those compounds that contain only carbon and hydrogen. That's it. There's nothing else to them. These can be classified broadly into 4 different types. We have alkanes, alkenes, alkynes, and aromatic hydrocarbons. Alkanes are the ones that we're going to start out looking at, and these are what we call saturated hydrocarbons. They're saturated with hydrogen, while alkenes, alkynes, and aromatic hydrocarbons are all unsaturated with respect to hydrogen. When we're talking about saturated, what that means is that you have as many hydrogens as you possibly can. There are no other hydrogens that you can insert in there. You can't manipulate bonds to add anything in. With unsaturated, you should be able to break a bond or make some sort of rearrangement where you could theoretically add more hydrogens in. These are on Blackboard, by the way, too. So if you feel like I'm flying through this, this is on Blackboard for you. Last night. Okay, alkanes, alkenes, and alkynes can be differentiated based on the amount of hydrogens in their molecular formulas. So alkanes, they have this generic formula of C to the N, H to the 2N plus 2. Alkenes are C to the N, H to the 2N. Alkynes are C to the N, H to the 2N minus 2.
Is that for the saturation, the little formulas?
The formulas help you predict if you're looking at an alkene, an alkyne, or an alkane. So, for example, if I wrote up this as a formula, and I said figure out if this is an alkene, an alkane, or an alkyne, what you would have to do is look at these formulas and figure out which one does this satisfy. Does this go into the alkanes, does it go into the alkenes, or does this go into the alkynes? So which one would this one be?
Alkyne.
So this is N equals 4. So
it would be an alkane.
Is this going to be 2 and is this 6 equal to 2N plus 2?
It would be
no. What about 2? Is it
2.
alkenes?
No.
It's the alkynes, right?
Yeah.
The 2N minus 2. So this is how you would use this information. Like you would be given, and I know that there's like one of these on the test. I forget what exactly it is. But if you were given that and asked, is this an alkene, alkyne, or an alkane? Which one is this one?
Okay.
An alkane. So these formulas can be used to predict from this very basic structure right here, what type of hydrocarbon am I looking at? Any questions on that? Okay. Simple math after what we've done in this class, right? Okay, so we're going to start off, like I said, looking at our alkanes. The simplest alkane is methane, and this is methane. So with the organic chemistry, basically you have to memorize prefixes, and the only way to learn these is to memorize them. And they're pretty simple because there's only 10 of them that you have to know. So methane is the main component of natural gas. That is the formula CH4. This is what we call our condensed formula. That's our structural formula, and this is a space filling model. I typically go and write condensed formulas just because it takes less space. But you are occasionally, like in lab today, you're going to be asked to draw some structural formulas. So you have to show the bonds and how they are formed around that carbon. A structural formula is like a Lewis structure, but it typically depicts bonding electron pairs as dashes and omits lone pairs. So we don't show lone pairs on structural formulas for organic compounds typically. We kind of just leave those off. The next one is ethane. Ethane has 2 carbons. And the formula for this is C2H6. So we have our formula. There's our structural formula. Once again, it's expanded out. And we have our space filling model. Ethane is a minority component of natural gas. Then we have propane. Propane is the main component of LP gas, so liquid propane gas. This is what's in those propane tanks that people use. And propane has 3 carbons right next to each other. It's what we call a 3-carbon chain. The next one is going to be butane. Butane is a 4-carbon chain, and you can see they just kind of keep increasing in the number of carbons and hydrogens. Now that we're at butane, we can actually show you a different way of writing what's called a condensed structural formula. This is just a shorthand way of writing the structural formula, which has a lot of repeating units in the middle. So here with butane, we can write this out as CH3, and this would be CH2 times 2, and then CH3 in the middle. So what they do is they took those 2 middle C's that have just 2 H's, and they can actually pull those out and put them in this parentheses here. So it does this nice condensed formula for that. The structural formula, you can do the same thing. I don't typically write them like that. I'm not used to seeing them, or the structural formula like that. We usually do condensed structural formulas like this and kind of ignore that method right there.
So you would leave the M there? You wouldn't put...
You would put a 2. If this was butane, you would put a 2. If there was 3, you change that to whatever number it's supposed to be. Okay, as the number of carbon atoms increase in alkanes. Alkanes are normal alkanes. They're straight chain alkanes. So does their boiling point. So you can see the boiling points as we go down and we start adding on carbons. So we had our methane, which had our 1 carbon is negative 161.5 degrees. That's the boiling point, pretty low. ethane had 2, propane had 3, butane's 4. And now this gets kind of easy because pentane has 5, hexane has 6, heptane has 7. It kind of goes to prefixes you should know. And we go up to octane. Octane's boiling point is 125.6. So based upon the number of carbons in a chain, you should be able to deduce just how many or how high the boiling point is. You should be able to say, okay, I have 5 carbons in this chain, so my boiling point is going to be quite a bit higher than like my 1 carbon chain. Methane, ethane, propane, and butane are all gases at room temperature, and then pentane is where we switch to a liquid at room temperature. Alkanes composed of carbon atoms bonded in a straight chain without any branching, like the ones we've seen, are called normal alkanes or N-alkanes. That's their abbreviation. In addition to going straight chain, we can also see branched structures called branched alkanes, and then we also we kind of rename them. We put this iso in front of it. So the simplest branched alkane is what's called isobutane. Isobutane and butane are isomers. Isomers are molecules with the same molecular formula but different structures, and because of their different structures, they have different properties. So if we look at isobutane, isobutane has that branch where that carbon drops down. This one has different structure or different physical properties than the actual butane did. Now, based upon your knowledge of the intermolecular forces, which one do you think is going to have stronger intermolecular forces? Will it be this one, or will it be that one? What do you think?
Well,
This straight chain right here, or that one right there? Which one do you think is going to have stronger forces?
the straight chain, because they're more tightly compacted. Like these are more branched out.
What? Oh, that'll fit. Okay, so our straight chain so our straight chain one looks something like that. So that's our straight chain. And this is our branch. So what were some of the things that we talked about intermolecular forces? What were some of the factors that influence intermolecular forces? The what?
Polarity.
Polarity. Okay, what else?
How close the two bonds are, like how close the two atoms are together.
Okay, the closeness of the two atoms. What does that do?
Like the radius too.
The size, the atom size. Okay. So when you have things that are, when you're talking about something that's a straight chain like this, how do you think that, we're looking at nonpolar molecules, right? We all see that?
Mm-hmm.
So when we're looking at nonpolar molecules, something like this, how do you think the electrons from neighboring carbon atoms are influencing each other? Do you think that one molecule of this could come up, pretend this is another molecule of that, do you think that they could come up and get pretty close to each other? What do you think? They can influence the electrons of each other pretty easily? What do you think? Is there really that much, how much shielding is going around on these carbons right here? Not that much. There's a few hydrogens around them, right? That's about it. Whereas with this one, what if you had two molecules that look like this with some, I guess I could throw the hydrogens on real quick. But you have a bunch of hydrogens. Okay, so here we have, you can just kind of see, you can start to get a picture of how the hydrogens are going to kind of glom around these. For this one, do you think it's going to be very easy for some carbon to come in and try and interact with the carbon that's in here?
No.
Why not?
Because it's like the hydrogens are kind of shielding the carbons. That's kind of where I see it.
There's a lot more, it's more
Yeah.
crowded, right?
Yeah.
So if this is more crowded in itself, is it going to be very easy to manipulate the electrons in this one versus this one that's more spread out? Which one do you think will be easier to manipulate the electrons in, this one or this one?
Straight chain.
The straight chain, right? So does that mean it's going to have stronger or weaker intermolecular forces? If it's easier to manipulate them. Stronger. It's backwards of what you would think, yeah. So because if it's easy to manipulate them, it's going to have stronger intermolecular forces than this one over here. So that kind of gives you an idea. When you were talking about the differences in properties, that's why. We're looking at the ease in forming those intermolecular forces here. Okay, naming alkanes. In the nomenclature system, the IUPAC system, naming the alkanes, this is pretty simple. We're looking at the number of carbons in a chain. So if you have one carbon, the prefix is going to be meth. When we're looking at hydrocarbons that are saturated, when we're looking at alkanes, the ending for an alkane pretty simple, always ends in ane. So if you have a hydrocarbon chain with one carbon in it, it's going to be methane. If there's two, it's ethane. 3 is propane. 4 is butane. 5 is pentane. 6 is hexane. So it just goes on, and up to, you just need to know up to decane. So once we get to 5, these are all prefixes that should be familiar. It's the 1, 2, 3, and 4 that usually kind of throw people off. But they're pretty simple once you learn. The prefix is determined by looking at the number of carbon atoms in the base chain, which is the longest continuous chain of carbon atoms. And this will be important as we start expanding to the type of work, the organic compounds. Groups of carbon atoms branching off the base chain are called alkyl groups and are named as substituents. So these are some of the substituents. You don't need to memorize anything past like the butyl one. I don't use isopropyl or any of those. I'll leave that for OChem later. So just the methyl, ethyl, propyl, and butyl. And if you'll notice, a methyl substituent only has 1 carbon, an ethyl substituent has 2, a propyl has 3, and a butyl has 4. So it's just like what we talked about with the naming of the chains, except these are going to be substituents. A substituent is an atom or a group of atoms that has been substituted for a hydrogen atom in an organic compound. Okay, so to kind of give you an idea what we're looking at here. If I wrote this on the board, and I asked you to give me the name, what would you name this?
Well, it has 6 carbons, so the prefix would be X.
And then is it saturated or unsaturated?
It looks pretty saturated.
It's saturated. How can we tell it's saturated? What do I look for to know it's saturated?
Each carbon is paired with a hydrogen.
It's all paired with hydrogens. Are there any double bonds in here?
No.
No, it's all single bonds. That's the biggest clue. All single bonds is going to be saturated. So if it's saturated, that means it's an alkane. It has 6 carbons, so what do we call that?
Hexane.
Hexane. Our prefix for 6 is hex, so we call this hexane. Now, when we start talking about these substituents, let's say I replace one of those hydrogens there. And I did something like this. Now I have a substituent on here. When I do this, I now have this branch. This is what we're talking about by substituent. And we'll go over how to name these in a few minutes. But now, if you look, I have 1, 2. When I'm numbering these, you have to be a little bit more careful when you do it. We said that it's the longest carbon chain. So when you number these, you have to figure out what way gives you the longest carbon chain. Because I have 6 that way. If I number it a little differently and go down this way, how many carbons do I have in that chain?
7.
7. So my longest chain is actually going this way. So sometimes it's a little tricky because we have to, it might look visually like, okay, that's supposed to be the parent chain, but you actually have to go through and count it with the bend and make sure that you actually have the longest chain there. Okay, in addition to alkanes, we have alkenes and alkynes. Alkenes, these are hydrocarbons containing at least 1 double bond between carbon atoms. Alkynes contain at least 1 triple bond. So an alkene it's easy to name these. It's the same thing where we're using the same prefixes as before. You're looking at the number of carbons in the chain, And this time, instead of using ane as an ending, you use ene as an ending. And for an alkyne, what do you think you use as an ending? Ine. So you just use the ine as an ending. So for an alkene, an example of an alkene might be something like this right here. This is ethane. Ethene, it has 2 carbons, so it's eth, and then since there's a double bond, you have the ene ending, so this is considered ethene. If I have this, that is ethyne. So that's just the difference, is there's a triple bond there, you have 2 less hydrogens there. So you're just changing that ending with the naming of it. You're just that ending of the name tells you if you have single bonds, double bonds, triple bonds, and what exactly is in that compound. Once again, remember that alkenes have that formula C to the N, H to the 2N, and then alkynes are C to the N, H to the 2N minus 2.
I noticed for the prefix 9, it's non. Is it different? So it's
Like nonane, nonine, or nonine.
Right, because I remember before it was nona. Is it different? Or
like
was it? Yeah, was it nona? Or nona?
Where for
No.
it's the same page.
Yeah, I think
Or am I just off?
Oh, are you talking about like from when we named
Yeah. So it's
molecular
different?
compounds? Yeah, it's just none.
Okay.
That's what you're going to use for that one. Okay, let's see, where do we go? Okay, here we go. The simplest alkene, once again, is ethene, also called ethylene. So you might, if you ever hear of ethylene, that's the same thing. The geometry about each carbon atom in ethene is trigonoplanar, making it a flat, rigid molecule. Ethene, this is kind of interesting. It's emitted by ripening bananas. So that's one of the tricks that stores use to ripen bananas, is they will spray them with ethene. It acts as a chemical messenger, inducing bananas in a bunch to ripen together. And banana farmers will usually pick the bananas green, so that way they don't bruise as easily. And then when they arrive at the destination, they're gassed with this ethene to initiate the ripening so that they will be ready to sell. So something that I did not know before I started teaching this class. The simplest alkyne is ethyne, also known as acetylene. So acetylene torches, this is what you use. The geometry about each carbon atom in ethyne is linear, making it a linear molecule. So that is ethyne. And then here we have a few more of the basic alkenes. We have propene, and then we get down to butene. Now, with butene, there's a number before the butene. Does everyone see that number? It says 1-butene. Mm-hmm. This number is used to designate exactly where this double bond is located. So what they do is, because this double bond is attached to the very first carbon atom, we call it 1-butene. If I had this right here, how many carbons are in my chain?
4.
There's 4. So this would also be a butene, right? But where is that double bond located?
2.
2. So this is going to be 2-butene. So that 2 lets us know where that double bond is actually attached to. So when you see these numbers, that's what that number means. Once again, same thing down here with 1-pentene. That 1 tells you that the double bond is located on the first carbon atom. 1-hexene, that double bond is on the first carbon atom.
Why doesn't propene say 1?
What is it, what?
Why doesn't propene say 1?
Okay, so let's pretend it's drawn like this. Okay, so it's drawn like this. What happens if I just flip this around? Does it look the same as that up there?
Mm-hmm.
Yeah. So this is still carbon 1, 2, and 3. So that this double bond is always going to be attached to the first carbon, because you just flip it around. It's like they have.
Okay.
So they have it drawn like this, right? Yeah. If I just flip it around, it's the other way. So it's always on carbon 1. It doesn't matter. You don't have to number it, because it's you can just flip it around. So there's that one does not have to be numbered. if I were to do this with a different one, like if I added on another carbon atom here, now I have to designate that it's on carbon 2 because now it's on the second carbon atom. So this one could move around between the second and the first, but notice it's never going to be on carbon 3 because once again, if I did it over here, all I have to do is flip it and it would be carbon 1 again. So if they're symmetrical, you have to be careful. You always, you always number chains starting where the functional group, which here is this double bond, is on carbon 1. So you always start numbering, like I would number this carbon 1 because it has a double bond here. So that always takes precedence.
So it seems like when it goes above 3 carbons, that's when you really have to start identifying.
Yeah. Okay, and then here's the same thing. This is just with the triple bonds. So these are alkynes, and most of these, like it says here, they're just in gasoline and minority components. They don't really have any other functional use that we use on a daily basis. So we have our ethyne, propyne, butane, 1 butane, 1 pentyne, and 1 hexyne. Once again, you have to designate where those triple bonds are after you get to the butane point. Okay, hydrocarbon reactions. One of the most common hydrocarbon reactions we've already talked about, and I think beat it to death by this point, is combustion, where you have the burning of hydrocarbons in the presence of oxygen. Alkanes, alkenes, and alkynes all undergo combustion. Remember, in a combustion reaction, our products are always what?
Carbon dioxide and water.
Carbon dioxide and water, always. Unless it's incomplete combustion, which we're not going into here. Hydrocarbon combustion reactions are highly exothermic. They emit large amounts of heat, hence the use of gasoline. This heat can be used to warm homes and buildings, also to generate electricity or to expand the gas in the cylinder and drive a car forward. So here's a couple of the hydrocarbon reactions. You don't have to understand all these, just understand like the definitions of them, if that makes sense. So in an alkane substitution reaction, one or more hydrogen atoms on an alkane are replaced by one or more other types of atoms. Most common substitution reaction is what's called a halogen substitution. So in a halogen substitution, you would take something like methane here, react it with chlorine gas, and what happens is a hydrogen that's on the methane is replaced with a chlorine atom. And so over here, this is what we call chloromethane is formed, and then we have hydrochloric acid over there as byproducts as well. So substitution reaction, a hydrogen is replaced with something else. That's what you basically need to understand from that. This is the condensed formula of it down here. Questions on that?
All substitution reactions are going to do that. They're going to replace a hydrogen,
with something else.
It doesn't have to be chlorine.
It could be any, like those are what we call halogenations. Okay. So a halogen will replace a hydrogen with one of the halogens. Alkenes and alkynes can also undergo addition reactions. And here what happens is that the atoms will add across the multiple bonds. So if we look at ethene, for example, it will react to form dichloroethane. So here you have ethene with this double bond. You're going to get a chlorine added to the left-hand side and to the right-hand side. It adds to both sides of the reaction. So that's why you see over there, there's chlorines on both sides. It's attached. There's a chlorine attached to this carbon, and there's a chlorine attached to this carbon. Whereas with ethane, the halogen is just added to one side. It doesn't do both. So the alkanes, it just adds to one side. Alkenes and alkynes, it adds to both sides of that bond. Alkenes and alkynes can also add hydrogen, and these are what we call hydrogenation reactions. Hydrogenation reactions convert unsaturated hydrocarbons into saturated ones. Vegetable oil, this is an unsaturated fat. You can hydrogenate it. That's what those partially hydrogenated oils that we always hear so many bad things about, this is where that comes into play. So vegetable oil is unsaturated. It contains double bonds, and they tend to be liquids at room temperature. When you hydrogenate them, then you form a saturated hydrocarbon, which is solid at room temperature. So if you think of the fats that are in your household, butter, what is it, solid or liquid at room temperature?
Solid.
Solid. So do you think it's hydrogenated, it's saturated or unsaturated? Saturated, right? Whereas if you look at like your canola oil, olive oil, all those, what are those going to be?
Unsaturated.
Unsaturated,
Does
right?
the body saturate them?
Is what?
Do they become saturated in the body, like during biological processes?
They can be. They're broken down further through different processes. It depends on what it's being used for at that point. So once again, is it going into energy? Is it going to be stored as fat? Is it going to be stored, what is it going to be stored as? So it depends on what your particular body needs it for, which is where the biochem comes in.
I didn't know that.
So yeah, this is kind of where you start to understand some of what you hear in the everyday world, because how many of you guys have heard of trans fats?
Yeah.
And that's one of the things we're going to talk about is what trans means. Does anybody know what trans means? When I say trans fat, do you understand anything about that?
I just know they're bad for you.
It's like everyone's like, oh, it's trans fat. Well, what does that mean? You're going to find out in a few minutes.
We'll have a new basic fad.
Okay, so by means of hydrogenation reactions, hydrogen is added across those double bonds and converts the unsaturated fat into partially hydrogenated vegetable oil, which is a saturated fat, which tends to be solid at room temperature. So basically, hydrogenation, if you were to look at that, if we were to just say, once again, take ethene, we could take our ethene, and you would add hydrogen to this, and it would just form ethane. So it's adding a hydrogen to both sides of that bond, just like the halogenation, where you add a halogen to both sides. The hydrogen goes to both sides of that bond. Okay, so to summarize, all hydrocarbons undergo combustion reactions. Alkanes undergo substitution reactions. Alkenes and alkynes will undergo substitution and addition reactions. So they will add those halogens and hydrogens to both sides of the double bond. Another type of hydrocarbon that we have is what's called the aromatic hydrocarbon. And in the mid-1800s, chemists were trying to determine the structure of a particularly stable organic compound called benzene that had the formula C6H6. Benzene now is known to be carcinogenic, so these poor people who worked on it, you can thank them for their sacrifice. So this guy had a dream, apparently, where he envisioned chains of carbon atoms as snakes. And these snakes danced. I know, it's just weird how these happen. You guys in your dreams are scary. I know. They danced before him and then twisted around and bit its tail. Based on that vision, he proposed the structure of benzene. And of all things, he was pretty much right. So he had the structure of benzene that he proposed, and this was what he proposed. Now, if you look at benzene, is it's a 6-member carbon chain that is cyclical, and it has alternating double bonds. And these are the two resonance structures of benzene. So benzene has resonance. Now, when we say that something has resonance, we also said that it introduces stability into it. It's a very stable compound. Benzene doesn't exist as either one of these structures. It more accurately has 6 1.5 bonds. It's not like a double bond. It's not really a single bond. It's about 1.5. So it's distributing those electrons throughout this whole molecule. So you will actually see, when I draw benzene, I draw it like that. And that means that those electrons are delocalized. They don't really belong to any particular carbon. We call them delocalized. They're shared amongst all the carbons in that compound.
But are they still shared with hydrogen?
The hydrogens all belong, but this just, when you start drawing them like this, it just assumes that there's a hydrogen attached to all these. So organic chemistry, we start to assume that you recognize, okay, my carbons have to have 8 electrons, so they're getting the missing electrons from hydrogen. Hydrogens a lot of times get left off. Okay, so here we have the space-going model for benzene. It's often associated with the shorthand notations right there, like I said, and once again, that one with the circle in it is what we kind of draw it as the most, and it's just easier to draw that way too. Each point in the hexagon represents a carbon atom with a hydrogen attached to it. Naming aromatic compounds, there's the aromatic compounds, they're a little bit different. We don't really have a conventional naming system per se. A lot of these just have to be memorized, and some of these have common names and they have IUPAC names. These are the IUPAC names right here. This is toluene, this is aniline. Aniline, notice, has an NH2 attached to that benzene ring. Here we have phenol, which has an OH attached to the benzene ring, and then we have styrene over here. These are things that just, once again, have to be memorized for familiarity. You can't really use any tricks to know them, you just have to learn them. Okay, questions so far?
The benzene ring, is that just something that Because it's a ring, you call it that, or is it?
Benzene would be this by itself.
But why did you call the previous slide that you were just on, those? Why did you call those rings benzene rings if they have like phenyl?
So there's a benzene ring attached to something else.
Oh,
This is a functional group attached to the benzene ring.
Okay, I thought
So
that was
yeah,
the drawing
it's benzene
of.
plus a functional group.
Okay.
Other questions on that one? Okay. All right, so functional groups are the next thing we're going to look at. And functional groups, these are families of organic compounds in which you have a replacement of a hydrogen with something else. So you have a hydrogen is removed, you have something else that comes in and takes that spot. A lot of times we'll use the letter R to represent a hydrocarbon group. So like here, this is a hydrocarbon chain, so you can have like CH2H, having like 10 carbons there. This R is that hydrocarbon group. This G over here is our functional group. It's going to represent those. What I expect you guys to be able to do is really just recognize functional groups and what that does to the ending of a name. You don't have to know how to name them per se, but if you see, like here, we see, okay, if you see something that ends in "ine," what do you know that tells you about that hydrocarbon?
Double bond.
Ine. Guanine. Triple bond, right? You know,
Yeah.
it's alkyne. Same thing with functional groups. When you have functional groups, it'll change this ending, and so you just need to be able to correlate that ending name, what that changes, with what functional group is actually in the compound. So let's look at some of these. So here we have alcohols, and alcohols have an OH on the end. So alcohols, when you're naming something, it changes that ending to OL. So alcohols in an OL, it changes the end of the hydrocarbon chain to OL as well. So here we have methanol, and you have to be really careful that it's an OL, not an AL, because that's something else. Methanol. Down here, we have 2-propanol or isopropyl alcohol, which we just call this 2-propanol, where once again you have the OH. So if you see an OH group on organic compounds, you know that the end of the name is going to end in OL. It just automatically changes to that. Okay, alcohols or organic compounds containing that OH functional group, they have the general formula R-OH. So R, remember, is that hydrocarbon chain. So a little bit about alcohol. Beer usually contains 3 to 6% ethanol. Wine contains about 12 to 15% ethanol, and spirits such as whiskey, rum, or tequila range from 40 to 80% ethanol depending on their proof. So a little bit about what that proof means. If you go out and are buying your alcohol and you're looking at proof and you don't know what it means, the proof of an alcoholic beverage is twice the percentage of its ethanol content. So if you buy an 80 proof whiskey, it's 40% ethanol. If you buy 100 proof, that would be 50% ethanol. So that's what that proof means. Ethanol is used as a gasoline additive because it increases the octane rating of a gasoline, which, remember, octane ratings are related to how cleanly it burns them. And it promotes complete combustion, reducing certain pollutants such as carbon monoxide and the precursors of ground-level ozone. Now, do you think you want to drink a 200 proof alcoholic beverage? No. Probably not. You value your vision. Okay, then there's isopropyl alcohol. This is stuff that most of us have in our house, probably, if you went to use it for any cleaning purposes. This is rubbing alcohol. It's commonly used as a disinfectant and sterilizes medical instruments. It should never be consumed internally as it is highly toxic. Just a few ounces can cause death, so not something to consume if you feel like having an alcoholic beverage. A third common alcohol is methanol, which is called wood alcohol. Methanol is commonly used as a laboratory solvent and as a fuel additive, and it is also toxic and should never be consumed. So just because we think something's an alcohol doesn't mean that it's safe to drink. How many of you guys like those little hand sanitizers? What kind of alcohol is in there? Any guesses?
Is there isopropyl alcohol in there?
Yeah, it's isopropyl. It sterilizes. I don't know if they're still doing it, but I remember, I think it was last year, hearing trends of kids drinking them.
Yeah.
Not a good thing. Not very dangerous, too. Not a good thing. Because they would feel good off of it, but then look at the, it's toxic once again.
Okay.
I know my baby likes to walk around and try and put them in her mouth, so that's always exciting, too. Okay, the next class of organic compound is what's called an ether. Ethers are organic compounds with the general formula of ROR. So there's a hydrocarbon chain, and there's an O that interrupts it from another hydrocarbon chain. So if you see two hydrocarbon chains with an O in the middle, that's an ether. The way these are named, pretty simple. There's an ether on the end. So if you see something that says ether on the end, you have an ether. Then also in front of that ether, it would actually tell you what groups are attached to the oxygen. So like over here, you have dimethyl ether. That means that there's a methyl group here and a methyl group here. This one's ethyl methyl ether. That means there's a methyl group on one side and an ethyl group on the other side. So it's pretty straightforward with naming these as well. But look for that ether name and tells you have an ether.
If you have something like carbon hydroxide, is that still a hydrocarbon or no? Like
Carbon hydroxide.
does that exist?
No. Think
Like
of how the carbon would have to try and obtain 8 electrons.
Okay. Never mind.
Methanol is as simple as it gets. Okay, so about ethers, the most common ether is diethyl ether. This is used as a lab solvent because of its ability to dissolve many organic compounds, and it has a very low boiling point, so you can evaporate it easily off of whatever it is you're working with. So the low boiling point allows for easy removal of the solvent. It was used as a general anesthetic for many years. This is very flammable, though, so not necessarily the best thing. When inhaled, it depresses the central nervous system, causing unconsciousness and insensitivity to pain. And it's decreased in recent use because a lot of the compounds have the same anesthetic effects with fewer side effects as well, so they don't make you as nauseous. This one is one that people wake up and they're puking their guts out. So better anesthetics have taken their place. Aldehydes and ketones. When you're looking at aldehydes and ketones, aldehydes have the general structural formula where there's a hydrocarbon chain over here, and that hydrocarbon chain has a carbon, and the very last carbon has a double bond to an O. So this is the last carbon of that chain has a double bond O, and then there's H attached to it. With a ketone, you would have a hydrocarbon chain over here, and then there's a carbon in the middle of it, someplace that has a double bond to an O, and then there's another chain to the right. So you would have 2 hydrocarbon chains. One of them has a double bond O. These are what we call carboxyl groups, as C double bond O. So one of them has a carboxyl group all the way at the end. The other one has that carboxyl group in the middle. So the kinetic structural formula for aldehydes is this RCHO, and for ketones is RCOR. And in ketones, that R group can be the same or it can be different on both sides, so it can change. Both aldehydes and carbons contain a carbonyl group up there. Ketones have the R group attached to both sides. Once again, I just kind of said all this. Look here. An exception to this is formaldehyde. This is an aldehyde with H atoms attached on both sides of the carbonyl group. So formaldehyde is the simplest aldehyde that you can get. It's 1 carbon. It's from methane. And you have just the C double bond O, and there's 2 H's here. There is no R group over on this side. So formaldehyde, how many of y'all know what formaldehyde is used for? Yeah, preservative, right? Nice little odor. Have y'all ever dissected stuff with formaldehyde used as a preservative?
No, I'm waiting.
It's fun stuff.
Oh.
Not wise.
No, because they had to ship them off.
Yeah, you get stomach pumps. Congratulations.
Yeah.
Yeah. Formaldehyde is also a carcinogen. They've discovered. So they don't use it as much as they used to in preserving things. So I know now that a lot of the animals that you get to dissect don't have formaldehyde in them so much. I think cadavers, they still use formaldehyde though. It stinks up the, when I was in school, it was all formaldehyde. Okay, so formaldehyde is a gas with a pungent odor. Those of you who smelled it, you know what I'm talking about. It is often mixed with water to make formalin, a preservative, and a disinfectant. It's also found in wood smoke, which is one of the reasons that smoking food preserves them. Formaldehyde kills the bacteria. So if you like your smoked meat, you're eating formaldehyde. I've ingested my fair share of it in my time. Aromatic aldehydes. So aromatic, remember, we're talking talking about things that have an aromatic ring, things that have benzene in them. There's a benzene ring in there. These will have very pleasant aromas. So aldehydes, once again, this is the class of compound that actually produces a lot of the scents that we're familiar with. So that's cinnamaldehyde. We have that benzene ring right here, and over at the very end, you have that aldehyde group, the C double bond O with the H. Benzaldehyde is over here, and then we have vanillin, which obviously is vanilla right there. Ketones can also have pleasant aromas. 2-heptadone, which is right down here. This is responsible for the smell of cloves. Carbone, which is in the middle right there, is responsible for the spearmint, and then ionone is for the smell of raspberry. So notice with the ketones, I said you have a carbon chain here, and you have a carbon chain over here, and then somewhere in the middle you have this carbonyl group. So it can fall in different places. It doesn't have to be just at the end. So carbone, we have it right here, and then ionone, it's going to be right here. So you can see those functional groups on those compounds. Carboxylic acids and esters, these are another class of compounds. Carboxylic acids will look like this. They have that C double bond O. So once again, you have that carbonyl group. This time, instead of an H or a chain being attached to it, there's an OH right here. This is our carboxylic acid. An ester, again, you have that carbonyl group, but now you have an O and an R. So this is an oxygen and then some other hydrocarbon chain attached all the way over there. So for carboxylic acid, the general formula for them is RCOOH, and for esters, it's RCOOR. Once again, R groups can be the same or different in the ester, so you might have two of the same, or you can have two very different. Carboxylic acids, these are weak acids, and they act as a weak acid in solution. Acetic acid is a carboxylic acid. We've talked about this a lot in this class. That is an example of a carboxylic acid. So they do act as acids. The most familiar carboxylic acid is ethanoic acid, which is known as acetic acid. It's the active ingredient in vinegar. Some yeast and bacteria will form acetic acid when they metabolize sugars in bread dough, and these are often added to bread dough to make sourdough bread. So if you've ever heard about sourdough bread, how they always have that starter is what has all this in it. It has the different yeast and bacteria that give it that flavor. Other common carboxylic acids are methanoic acid, which is called formic acid. If you've ever been bitten by an ant or stung by a bee, then you've had that put into your body. It doesn't feel good. Citric acid is the acid present in limes, lemons, and oranges, and then lactic acid is the acid that causes those nice muscle cramps that we all love. Then esters. Esters are best known for their sweet smells. Ethyl butanoate, so if you see the O8 at the end, we're talking about an ester. It's responsible for the smell and taste of pineapples. Methyl butanoate is responsible for the smell and taste of apples. Esters are formed through the reaction of a carboxylic acid and an alcohol, and then an important example of this reaction is actually the formation of acetylsalicylic acid. Say that 5 times fast. And that's aspirin. There's actually, most organic labs, you will synthesize acetylsalicylic acid. Acetylsalicylic acid. I'm not sure if that's the day. And that's synthesized from acetic acid and salicylic acid, which is obtained from the bark of a willow tree. Okay, next class. These are some of the more pungent smelling organic compounds, and these are amines. Amines are organic compounds that contain nitrogen, and the simplest nitrogen-containing compound is ammonia. Ammonia is probably the best smelling of the amines. So if that tells you anything. Obviously, you don't want to walk around sniffing a thing of ammonia all the time. Those are, a lot of times it's using smelling salts to get people conscious after they, knock their head, and there's a reason for that, because it's potent. Huh? Oh, yeah. It's stinky stuff. All other amines are going to be derivatives of ammonia with one or more of the hydrogen atoms replaced by an alkyl group. So these are named basically according to the hydrocarbon groups that are attached to the nitrogen and given the ending amine. So here we have trimethylamine. There's 3 methyl groups that replace each of those hydrogens. So we have trimethylamine. Over here, cadaverine. Any clue what that smells like?
Dead body.
Yeah. So cadaverine, hey, there you go. So this one, you have 2 amines, and in the middle of them, you have a chain of carbons, that 5-member chain of carbons in between them. So that's cadaverine, and then putrescine. Doesn't that smell? You can just imagine the smell of these by their names. So once again, you have the 2 nitrogen ammonia groups, but then you have the chain of hydrocarbons. This one only has 4, whereas this one has 5 in the middle. So these are some examples of some amines. Once again, amines are best known for their awful odors. When a living organism dies, bacteria that metabolize its proteins emit amines. So decomposing bodies have a lot of amines emitting from them. Trimethylamine causes the smell of rotten fish. Cadaverine and putrescine are responsible for the smell of decaying animal flesh. So that's what we're all going to smell like sometimes. Doesn't that make you feel better? Okay, questions so far? You guys are understanding why I'm like, this is an overview test, right? All right. Polymers. This is another class of organic compounds. Polymers are long chain-like molecules that are composed of repeating units. The individual repeating units are called monomers. So you have basically groups of monomers, small units that repeat over and over and over again to form a polymer, which is a long chain-like molecule. Synthetic polymers compose many plastic products such as PVC tubing, styrofoam coffee cups, nylon ropes, and plexiglass windows. Ethene, also called ethylene, remember, monomers can be made to react with each other, breaking the double bond between the carbons and joining together to make a long polymer chain. Polyethylene is the polymer that these form. So polyethylene is the plastic that composes milk jugs, juice containers, and garbage bags. And it is an example of an addition polymer, a polymer in which the monomers link together without eliminating any atoms. So they just basically break the double bonds. There's nothing eliminated. Some polymers called copolymers consist of two different kinds of monomers. For example, the monomers that compose nylon 6,6 are hexamethylene diamine and adipic acid. These two monomers add together by eliminating a water molecule for each bond that forms between the monomers. Polymers that eliminate an atom or a small group of atoms during polymerization are called condensation polymers. Okay, so here are some of the polymers that we have and some of their purposes. So the very top, you see this polyethylene that we talked about. That's the packaging in bottles. It's your milk, juice containers. Then we have polypropylene underneath that, which is in your kitchenware and fibers and appliances. Then the next one is polystyrene. There you see that we have that benzene ring. We introduced that aromatic compound down there. And that's in packaging, disposable food containers, and insulation. Then we have polyvinyl chloride, and that's in pipe fittings, clear films, and packaging. So those are all addition polymers. Remember, addition means that nothing is actually, there's no atoms lost. You just kind of get this chain added and added together. The next thing we have down here is the condensation polymers. So condensation, what do we know our byproduct is? If it's condensation, what was a byproduct? Water. So water's that byproduct. So with polyurethane, this is foam for furniture stuffing, spray-on insulation, automotive parts, footwear, water protective coating. Then we have our polyethylene terephthalate. And that's the tire cord, magnetic tape, apparel, soft drink bottles. Then down here was our nylon 6,6, and the reason it's basically called 6,6 is because you get this 6 in here. Home furnishings, apparel, carpet fibers, fish line, and polymer blends. So these are some of the polymers that you know that we actually use on a pretty much daily basis. Kevlar, that's another example of a polymer. What do we use Kevlar for? Bulletproof vest. Pretty important stuff, right? So Kevlar is stronger than steel. It's going to stop a bullet. Kevlar is condensation polymer consisting of containing aromatic rings and amide leakages. So amide, those are going to have nitrogens in them. The polymeric chains within Kevlar crystallize in parallel with strong cross-linking between neighboring chains due to hydrogen bonding. So based on our knowledge of intermolecular forces, do hydrogen bonds like to give up a whole lot?
No.
No, they're pretty strong. They're going to stay pretty compact together. This structure is responsible for Kevlar's high strength and its other properties, including chemical resistance and flame resistance as well. It's particularly well known for its use in bulletproof vests. So those hydrogen bonds are what is responsible for giving Kevlar a lot of its bulletproof resistance.
Can they resist gamma radiation as well?
I don't think so. I don't think the radioactivity is entirely different. Gamma radiation, really, the only way to protect yourself is really thick concrete walls, like really thick ones. These wouldn't do very much good if it was in a high dose. That's it. Ta. Well, I mentioned that I was going to tell you what trans fat was. I didn't have it in there, so I'll show you what trans fat is. We have time. Okay, so I mentioned I was going to talk about the difference between what a trans fat was versus the other type. This right here is what's known as a trans isomer. This over here is what's known as a cis. If you notice with cis, you have the two functional groups, or the substituents, the chlorine and the hydrogen. these are located on the same side of that molecule, whereas trans, they're on opposite sides of that double bond. Can you guys see the difference there?
Yeah.
So when they're talking about trans fats, what they're talking about is that they're arranged so that, in the case of these hydrocarbons, okay, let's pretend that this is our hydrocarbon here. If we were to look at the cis versus the trans form of this, this is our two different forms here. With our double bonds, you basically introduce a degree of rotation here. Or what will happen is that you'll have one form like this where you have the hydrocarbon chains both up on the top. This is what's referred to as our cis form. Down here, this is what is referred to as our trans form. So when they're talking about trans fatty acids or trans fat, they're talking about something that has this kind of chair-like, step-like movement here. That's the difference between a trans fat and a non-trans fat. I forget exactly why it is that these are worse for your body than these. I forget what the difference is in the body. I'm not a biochemist. But that's the difference between those two. So now you know when you hear trans fats, you can visualize the difference between trans and cis.
Could it be because
They're
harder to break apart because of the way that they're
the force
organized?
molecular forces.
I'm trying to think. I think that cis. Yeah, I think that cis is easier to react with. I'm having to go back about 20 years to my biochem class. I don't remember very much of it. It's been a long time. So I'm sure it has to do with reactivity. I just don't remember what the logistics is behind why it is. Yeah, go to the internet. Go Google it. Resources that I wish I would have had.
Extra credit?
No.
Okay, any questions?
What was that?
Any questions? We have like 6 minutes left. Something like that. A really small class today. I
So
guess
for
the
the-
exam scared a lot of people
For
away.
the exam, basically just memorize like the basics of naming, and we have
Very basics of naming, and then kind of the overview that we talked about with all the information from everything. So just general knowledge. I don't expect you, I'm not going to draw some huge compound on the board and say name, just very basics.
So then we don't know how to, like, do we know, like, the basics of naming, like, the alkynes and...
Knowing the alkanes, alkenes, alkynes, you should know how to draw those. And we're going to do that in lab today. That's actually what the lab is going over the basics of drawing those. And then knowing how functional groups, what functional group matches with the name. There's a table in your book. What? Yeah, table 18.7 actually has the functional groups, and then it shows you examples of the names. So that's going to probably be a very useful table to study off of. And that we will be doing in lab today as well. So that's part of the lab too. Other questions?
Yeah, so,
Yeah, next Tuesday is the test. That's part, yeah. And once I get the exams and grade them, I'll probably, hopefully by Thursday, I will be able to figure out what we're going to do about this last exam.
which is,
Huh? The exam from last Tuesday. See what happens with that.
we should do chapter 17.
Oh, I love nuclear chemistry, but we just don't have enough time. We have to take 151 for that.
I will eventually.
All right, then I guess we're done.
I don't. Oh my gosh! Apparently, sodium hydroxide can decompose.